Here is our ball and pipe air levitation system. This setup is using airflow for moving the ball inside the tube. By controlling the airflow, changing the speed of the blower, controlling the position of the ball is possible. I should mention that this setup is nonlinear. This setup is useful in educational application. Mechanical, electrical, and control engineering students can obtain benefits from different experimental scenarios by doing the experiments, such as testing various linear and nonlinear control theories. This is useful because students can experience the practical applications, so ball and pipe stand can be a good benchmark in this field. Now we are going to test a PID control strategy for positioning the ball. First, we insert the set point 25. Then we run the system. We expect the control system generates appropriate control signal and position of the ball would track the reference trajectory. Okay, it's done. Now we change the reference to 20. Click OK. As you can see, the ball is tracking the reference as well. As you can see here, the position is on 20. So we can understand that the control strategy is doing well. Now we are going to change the position again. We are aiming to put it on 27. We click OK. Here you can see the position of ball is set on 27, and here we can have it either in our simulation. Here is our PID block. You can see the parameters. Its main parameters are gain, the integral gain, and the derivative gain. Each of these have different effects on the response of the system. For example, by decreasing the proportional gain, slow response will yield, and of course, a better stability. And by increasing the P gain, fast response and instability is caused. Also, by increasing the integral term, it yields a decrease in the steady state error, but also can decrease the stability. But by decreasing the integral term, this can increase the steady state error. Either in D term, I mean the derivative term, it yields to a faster response, but even increase the stability. And by decreasing the D, we have all terms in vice versa. It means that it yields a slower response and decrease in stability. Okay, here we have proportional gain. We put it on 0.7. The integral gain is 1 and derivative gain is 1 as well. So we click OK, and you can see the response of the system. By changing these gains, you can see the different responses of the system. Now we are going to change the term derivative. Right now it's on 1. We put it on, for example, 0. We click OK. You can see that the system becomes unstable. And here you can see the graphs that's showing this phenomena. Okay, we are going to get back to our previous position. We put again the derivative gain on 1. You can see that the system is stable again. And the graph shows this too. Now we are going to change the other parameters, for example the proportional gain. We put it on, for example, 2. You can see that the responses is not suitable. It's unstable too. We can define different set points as our references for tracking projects. As you know, trajectory tracking can be used for teaching different application in control. Here in this project, we used sinusoidal wave reference trajectory. As you can see, the ball is tracking the reference trajectory.